was already introduced, and we have a group here at IIT Bombay, and my colleague at UT Dallas, Professor Rishabh Iyer. We've been trying to build robust techniques and compute efficient techniques for deep learning. And why is this of interest at all? Now, can you continue? You can continue seeing my slides, right? The slide, zonal
Yes, sir.
slides.
Yes, sir.
Okay. So why is it required at all? Nowadays, deep learning has basically proliferated everywhere. And this entire workshop is on deep learning. So what we'll talk about is subset selection for compute efficient training of deep neural networks. That's the first point. But this compute efficient training also leads to a byproduct, which is robust learning under robust optimization settings. However, there are also important techniques that do robust optimization as their primary goal. And then how do you put them together for compute efficient deep neural network inference? Okay. These are the three topics, and we'll, if time permits, we'll also talk about compute efficient feature learning. So deep learning has proliferated everywhere, and deep neural networks have become extremely data hungry. So on the left side, what you see is an image stating the power law, right? That larger, basically the data for training, larger the performance of the model. What you see on the right-hand side, though, is a specific example of a model called the ResNet model. You see how its performance improves with the increasing number of training images. But coming up with a large labeled label size is consuming and expensive, and also creates a major bottleneck for people in low resource environments, low new settings, right? Completely new setting. If you want to adapt, it becomes challenging. We have made several products around compute efficient learning, including surveillance products. If you want to deploy something in a particular surveillance setting, which is security setting of national importance, you may not get so much data out there to be able to retrain deep models from scratch. How do you learn with less amount of data, and how do you learn it efficiently? So continuing on this discussion, here's a specific example showing the compute costs of different supervised and semi-supervised learning settings. So training a wide ResNet model using something like fixed match on the CFAR 10, let's say with hyperparameter tuning. So you see that the costs are very high. Likewise, we have training BERT and transformer models. You can see both the training cost, the energy consumption, and lots of CO2 emission as well. The other issue is noise. So even if you manage to basically use the entire data set, what if the data set exhibits cues? And you can see for some tasks like face recognition, some kinds of faces, maybe white faces, white skinned images are very overrepresented. The darker ones may be underrepresented. So there's imbalance in the data and noise in the data, right? And this is this long tail phenomenon. There are lots of phenomena which are very less represented. Lots of places with very less information. Some places there's too much information out there. Likewise about species. Human beings think they are the most important species on the planet. And then there is actions also. You can see certain, even the state of the art benchmarks, they talk about certain actions which are very frequent, but really lots of actions are practically ignored with very few examples. How can data subset selection help, right? So the challenge is as follows. If I identify a 10% subset of the entire data set on which I can get the same amount of performance as the entire data set, obviously you'll get 10x faster training. But how do you identify that 10% subset, right? So all of us know the challenge that, it's really an exponential search problem. If to identify, um, so let's say I have the power set. Okay, you have n examples. So you have the power set, and what you're basically seeking is a subset U of the power set, right? So that can be very expensive to explore. So you don't want to just get the 10% subset, but you want to identify the 10% subset as efficiently as possible. Will a random subset work? Let's take this example, right? If I do a random subset, what would happen is that a random subset would represent lots of examples from class 0, few examples from class 1, and probably class 3 would get neglected. There's an imbalance setting. What we really want is what I have highlighted here. We want to represent all these classes well. So here you see almost 4 points picked up from each class. This is what we want. So if the training data is imbalanced or noisy, training a model on data subset that is clean leads to also robustness. You're fair to all the different regions of the data set. Likewise, you can have very high model inference timings. And you can see the model inference time for small gains in accuracy on some data set like image is significant, right? The inference time is in terms of gigaflops. So there's a marginal increase across as you go from one architecture to another, but the training time is increased disproportionately. Okay, so this is disproportionate increase in the training time. In the inference time. And that's because your models are becoming very complex and larger. So therefore, there is also need for identifying model architectures which are compact so that you can do efficient inference. What can lead to this compactness? The two aspects. One is you can remove the synapses, which is these connecting edges. You could remove them, right? So you see, for example, we have removed a whole bunch of these on the right hand side. We have removed this particular edge, and we have removed this particular edge, and so on. The other thing we can remove are nodes. So you can see a node here has gone missing. So removing neurons. This is also known as architecture search. Now, let's start with efficient learning. What are the subset selection strategies which can lead to reduced training time, reducing energy consumption, reducing training cost, and also reducing the CO2 emissions? And the 4 methods we'll talk about: Craig, Glister, GradMatch, all from our group, and then retrieve as well. I'm going to motivate it. There's going to be a little bit math here. I'm assuming most of you have already got familiar with deep learning. So the idea behind Craig is that you want to identify a subset of the entire data set. Okay, here a star is a subset of the entire data set V. In what sense? Well, you're going to identify the subset that approximates the gradient of the entire data set. So here's a full gradient, and here's a gradient on the subset. There's a bunch of weights associated. All of us know gradient plays a very important role in the model, right? So what we want to do is identify a model such that a subset of the data set, when you take the weighted sum of the gradients on that subset, you're approximating the gradient of the entire data set well. Now, let's understand a little bit more jargon here. So here, what you see are these representative points for each subset. Okay, the things that are crossed out here are the representative point. Okay, so broadly speaking, let's think of a point here as I. Okay. Now for this point I, this cluster or the centroid which it belongs, call it pi I. Now we are talking about the pi I centroid in the sense of the distance of the gradients. So for pi I is what? Pi I is that point which is closest of all the j points in S, this closest in terms of the gradient. The gradient of f at the point I is closest to the gradient of the f at the point j. So that point j is the pi I. Okay. So think of this as the membership, the class centroid to which I belongs. Now there is another notation here. There is gamma. What is gamma j? Gamma j is the number of points like I which contribute to this centroid. Okay. So this is the contribution number of i's belonging to pi j. I mean, or j is belonging to pi j, whatever, right? I is belonging to a particular pi j. That is basically the gamma j. Okay. So what we are doing here is we are saying, okay, the full gradient should be approximated by the weighted sum of gradients in a subset. And let us identify such a subset. Now, what does it turn out to be? Well, it turns out that if you just expand the gamma j, with the gamma j is explained here, then basically you're summing over all the points in the set of the difference of the gradient of the point I from the distance of the gradient at pi I, right? Take the gradient of f at I, take the gradient of f at pi I, right? And you want to minimize this difference. This turns out to be something that I can upper bound. What can I upper bound this with? Well, instead of doing it for all the points pi I, I'll say, well, let me just find the j in S which is closest to the I. So that's an upper bound. So this turns out to be basically facility location problem. We are basically solving a problem called the facility location problem. The facility location problem, okay, as I've highlighted here, can be cast as a submodular maximization problem. Now, I will not get into the details of submodular maximization problem, but I just want to make an important note here. Submodular maximization under some set constraints, we'll call cardinality constraints, has very good greedy algorithms. Has efficient, if rather effective. When I say effective, good approximation, greedy algorithms. And what's the greedy algorithm? It just says, okay, the greedy algorithm is very simple, right? That you pick the next, the point that minimizes this distance the most as the next point. Keep doing that, keep doing that. So the greedy algorithm makes a lot of sense because of that reason. And what is the good approximation we are talking about? The good approximation is a guarantee 1 minus 1 over e. Though, well, e is the natural logarithm, base for the natural logarithm. Now it turns out that in practice the approximations you get are even better. Okay, the simple idea. Let's just try and now understand the effect of some simple strategy like this. Okay, you can see that on a standard data set like MNIST, if you were to randomly select points, right, the green one is random subsets. Just find random subset of points. You find that, well, it is not able to go beyond a particular accuracy. You need the entire data set to actually reach the accuracy that is being sought after. That's the orange curve. However, random is very effective. You don't need the entire data. You just find a subset of the data. What turns out to be, however, a good trade-off between random and full is the Craig algorithm, where you are not identifying a random subset. You find that subset which matches the gradient well in facility location sense. And there you are able to, however, match up the accuracy of the full, that is all data, with 2x to 3x speed up, which is a good speed up, right? 2 to 3 times faster you can get the same accuracy, and you can see that's why the curve is always above. Okay, so this was published in 2020, but now let's talk about some advances we made over the last 1.5 years. We said, well, why not tackle the problem a little bit more principally? And what is the principle here? We are saying that identify a subset of your training data, S subset of you. This identify a subset of the training data such that when on that subset, I maximize the likelihood of my model with respect to a validation set V. We always have training and validation set. So U is training set. Identify a subset of the training set S. Based on S, you estimate the parameters theta. And when you apply this on the validation set V, your outer likelihood should be maximized. This is outer likelihood which is applied on V. So this is called a bi-level optimization problem. You have put a cardinality constraint here. You're saying that I don't want the size of the subset to exceed a particular threshold. So that's called cardinality constraint. So this, for general loss functions, the inner loop is going to be very expensive. So by inner loop, I mean this part. This is a very expensive step. Because every time you identify a subset, I'm going to estimate the parameters theta. Okay, so the inner loop is expensive. And in some sense defeats the purpose of selecting a subset. I have a 10% subset, but to find that 10% subset, I have to keep computing theta, identify another 10% subset, find the theta, and then somehow over this large search space, find the right 10% subset. Absolutely defeating the purpose, right? You might as well fall back on Craig, which I described earlier. However, there's a better strategy. What you do is you approximate the inner optimization problem solution. So in the previous slide, you saw that I had on the validation set LLV, and on the training set, I was trying to estimate the theta on the subset S. Now we are saying that this component, the parameter that you're getting, sorry, it should have been argmin. Let me just put that argmin here. What we had was, or rather arg, I don't remember what I used, argmax, because we're looking at likelihood, argmax over theta. So this argmax over theta of LLT, you approximate. Don't use the exact version. What is approximation you're using here? You're saying, well, let me do the single step gradient. Imagine that I started with the previous theta and did a gradient descent update step on that subset S. Now this is what you do. So if you go by this strategy, you start with some random parameters and then find a subset, and on that subset you do a gradient descent step. Now the question is, even with this, how do you do the subset selection? So we go one more step. During subset selection, we want to have speed up. So we say that this entire outer objective, which I had written down here, this itself I'm going to approximate using Taylor series. So while we approximated the argmax over theta in the previous step, We are going one step further and we are saying, well, this entire expression of likelihood with respect to the validation set, that itself I'm going to approximate as the likelihood with respect to the validation set on theta plus a dot product term involving the likelihood on the subset S with the dot product of the theta on the validation set. In some sense, this is measuring alignment. It's like measuring how close the subset S is with respect to your validation set in terms of the parameter theta, the Taylor series approximation. Why is this interesting? It's interesting because, again, when the validation log likelihood function is, say, the negative logistic loss or the negative squared loss, negative hinge loss, negative perceptron loss, or negative cross entropy loss, the optimization problem again becomes an instance of a cardinality constraint submodular maximization problem. I already said for submodular maximization problems, there are greedy algorithms which give 1 minus 1 over E approximation guarantees. So now we have an advantage. We don't have to keep evaluating for each subset that you select the entire parameter estimate. You've now done this gradient descent, not only gradient descent, single gradient descent update approximation, but also Taylor series approximation. So this turns out to be much faster. Okay. Let's look at the results. So I'm going to compare against what was presented earlier in the form of Craig. Okay, here's Craig. And we saw that Craig gave you 2x to 3x speed up. But Glister can give you 7.2x speed up if you just go for 10%, right? 10% data set, you find some 3% drop in accuracy, okay, which is fine. But if you go for 50% data set, you'll get hardly any drop in accuracy, 0.2%. So depending on how much drop in accuracy you're fine with, you can be as aggressively pruning. But the point is, even for just 3% drop in accuracy, you get almost 10% speed up. And it's, of course, significantly outperforming Craig, which was described earlier. Why? Because it has taken a more principled approach. We then move to another approach, which you'll find that does better than even Craig and does better than even Glister. And that's the idea of grad match. Now, grad match is in some sense is connected to Craig, which we discussed earlier. That's the first approach, which is just okay, and then Glister, and you'll find that this gives you both advantages. It also has some interesting theoretical standpoint. See, any adaptive subset selection framework has an additional error term, which we'll see in the next slide. And that error term we try and directly minimize in the form of the gradient matching technique that we'll talk about. That's grad match, gradient matching. The short form is grad match. And we have given reference to the paper, our published paper from last year on this. So what is it doing? It's trying to select a subset that minimizes the convergence error term due to training on a subset. Now, Craig had this magical term gamma. We're going to try and learn that as well. So over to grad match. So here's the idea. You're trying to identify weights and subsets. So I'm trying what we were referring to as gamma. Now you're trying to talk about them as weights. Now it turns out that under certain different conditions, Lipschitz continuity it's a condition on the loss. Lipschitz smoothness is another condition on the loss. Strong convexity, etc., etc. But under many conditions, there's one interesting term that is sticking out, and that is this term, which I'll talk about in the next. So what we observe is the model training on any adaptive subset selection results in this additional error term, okay, which is added to the convergence rate. Point is, can this error term itself be minimized? Can it be made as small as possible? Okay, and what is this error term? This error term is just saying weighted sum of the likelihoods of the subset should be as close as possible to the overall gradient. Weighted sum of the gradient should be similar to the overall gradient. This is for a subset xt. Now here the w itself is not predetermined. We have the w itself is part of the optimization problem. Okay, so we try to learn the w's as well. Okay, so we want to learn both the w's and the weight and the subset x. And it turns out that this resulting problem is approximately submodular. Okay, so I mean, I have not described submodularity, etc. But approximate submodularity is basically a diminishing returns property, and approximate and just like submodularity has some very good greedy algorithms, approximate submodularity also leads itself to some nice greedy algorithms, which we'll not get into. Okay, and to estimate the parameters w in conjunction with the greedy, this is a greedy algorithm. Okay, so what you see here is a greedy algorithm. You're greedily picking the element to be added which maximizes some residue r, right? So this is greedy step. And what is that r? R is the gradient of the error. Okay, and once you identify the element e, then you're solving for the weights is another kind of linear. This is a linear regression problem. Okay, now how does it benefit? So it's even more impressive. So you can see that for 10% data set, you can find the speed up is less 7, and the test error is like 2.8. So it's improved even over Glister. Likewise, we have presented on a couple of other data sets. CFAR 100 is another data set. ImageNet, we have similar observations, and overall it gives you better performance than even Glister. We extend all this to another very important setting, which is semi-supervised learning. So often you're not just given labeled data, you have some labeled data, but you have a large amount of unlabeled data as well. Of which this labeled data is just a subset, right? Unlabeled data, U. The goal here is I'm trying to identify a subset of this unlabeled data which should be used in conjunction with the labeled data. Now, obviously, I don't want the entire unlabeled data because it might just have a lot of noise. It's just inefficient as well. Again, as in the case of Glister, the training the model to convergence in the inner loop is expensive. So what can we do? Again, as before, we can resort to two things. We can do a one-step gradient approximation, and we can also use Taylor expansion. Okay, so there are two things we do. One step, like before, we do this approximation of the inner optimization problem by taking a single gradient step towards a semi-supervised loss descent direction. So that's the first one. And the second is you also do a Taylor series approximation on the outer semi-supervised loss. So this is the need, this reduces the need for multiple forward passes. That's very important. The entire idea of using the Taylor series approximation so that you can train take this likelihood on the subset S to be a constant means that the forward passes, that is, for every subset when you select, you have to do again the inference that you can try and avoid by using this first order approximation. This is called retrieve, and this retrieve achieves speed ups of 3x with just 0.7 drop in accuracy. It's very impressive. Or if you want no accuracy drop, then you get a smaller speed up, which is still impressive, 2x. Okay. So what we have talked about is efficient learning. Next, we'll talk about robust learning. You not only want to reduce training time, but now you also want to be robust. Why we say robust is because, as I pointed out earlier, maybe the entire training data set is not worth it. You may want a subset of the training data which is noise free. If you know support vector machines leverage that in the past. They found those support vectors. If you are trying to classify positive points from negative points, so instead of taking all the points, what you would do in the case of support vector machines, you could have these points as well. And let's say you have these negative points. So instead of picking all the points to ensure robustness, you determine the supporting hyperplane, so to speak, something like passing through these blue points on this, say in this the boundary kind of points, and these pink points here. This is a support vector idea. Now, can this be done for deep learning models when the objective is not even support vector? So there are the method that I talked about, glister, grad match, retrieve, all of them generalize well. They can be reapplied. They are all reused here. In addition, I'll talk about one new method called crust, which also gives you robustness. So what's the idea behind crust? Idea here is that you want to minimize the squared loss on noisy label training data. So this label data can have noise in the form of the Ys. And as I showed in the previous slide, here are examples, right? It's not every point is not worth it. So what will be the noise for us? So the noise could be all these points. Let's just annotate them. So imagine these points which we were not terribly happy about. This point lying on opposite side. These points are lying on opposite side, right? So this is what we mean by noisy label training data, that the Ys could have noise. They could be on the wrong side, for example, from the point of view of the model. So you're trying to optimize the squared loss by gradient descent, say, right? So this is a squared loss. Let's say you optimize it using gradient descent. So when you write down the step, now across all the weight parameters, across all the classes, you have this interesting matrix called the Jacobian matrix. Now, what is a Jacobian matrix? It's basically nothing but a stack of all the gradients across all the weight vectors for each class, say. Now, this exhibits a low rank structure. What it means is that there should be more signal and less noise that you want to extract. What is a signal? The signal you would expect to be low dimensional, clean. This is what we expect from a signal. Clean, large singular values, and so on. I mean, if I want to take a road, take a car from, say, Pune to Mumbai, I could go through the hills, right? But there's too much of noise. But if I go through the expressway or a highway, it's well set out. There is less uncertainty that I'll reach the place. But that is the information space. The highways are the information space from the point of view of travel. The nuisance space is all the hills, etc. Now it turns out that the road is low dimensional. It doesn't have too many bumps. Whereas the nuisance space is high dimensional. It's all over. The labels can be noisy in the nuisance space. And that reflects in an important thing. With the Jacobian matrix, you can have small singular values in the nuisance space. So that's important. These two are important from the point of view of the Jacobian matrix. The fact that in information space you have large singular values, and in the nuisance space you have small singular values. So crust exploits this. And how does crust go about this? Yeah, it says that data points with clean labels will cluster together. Data points with noisy labels will spread out. So idea is again facility location or k-medoid clustering, which are basically analogous. So what you're trying to do here is for each point j in the subset of points, you find For each point I, you find the point J in the subset of points which is closest. So you're basically looking at this S as your representative subset. So let's say this is a set of points. This is the S. For every point, I'm going to now identify the point in S that is closest. Okay, so this is the closest point from this point in V. From this point in V, this may be the closest point in S, and so on. Okay, these are points in V, whereas these are points in S. So this turns out to be again a submodular maximization problem. And also, Crust does something more. It does this on a per class basis, identifies this k-means clustering to identify the cluster on a per class basis, and it also mixes up points within each cluster, something we'll not go into. It's to basically further eliminate noisy labels. And you can find that on, again, standard data sets. Because of robustness, now the concern is no longer about speed, but under different noise ratios values. And you can have symmetric noise where your noise is for each class same. Asymmetric where you have more noise for some classes, right? More noise in certain classes. But in all settings, Crust is shown to improve performance overall. So there's the last row that you see is the performance with Crust, which is impressive. However, Crust never focused on efficient learning. What if we repurpose Glister that I talked about, the bi-level optimization for robust learning? Well, you can basically use a clean set free of class imbalance and noise, let's say as validation set in Glister. Right? So the validation set becomes very important. So you might recall that we had the LLV and argmax over theta of LLT, theta comma S comma V, right? Now what we are saying is this validation set plays a very pivotal role in ensuring that you generalize well. As long as the validation set is noise free. So based on the validation set which is noise free, you identify a subset of the training set S that yields to best performance. And here again you can see that just by using validation set you get better improvement. I mean, a lot of improvement. I mean, we have different versions here of Glister, which I'm not going to detail. So you can do regularization of Glister using random clustering or facility location based clustering. But in all cases, whether it's the black or the yellow or the green, you'll find that you're doing significantly better, right? Then obviously the random, and also better than full. It means you've become robust. Likewise, we have results for grad match. In grad match, when you're doing gradient matching, you can say that I'm going to identify on the full data set the sum over all the gradients to be as small as possible, to be as close to as possible to sum over all the gradients in the subset weighted by this gamma or W. We are using W eventually. Now, if this I came from a validation set, then again we get robustness. If you're trying to match not the gradient on the training set, but the gradient on the validation set. So clean set full of free of class imbalance and noise when you use it as validation set. Then what happens? Again, we find that all these variants of grad match, one in blue, these are the variants of grad match. And they're significantly better. Right, they're all of them are like lower. All these, the ones below, because error is low. I mean, you can do this with class imbalance setting as well, where there's some classes are more dominated. Okay, so likewise for semi-supervised learning, we find that there's consistent improvement in accuracy. Speed up is already there, but in addition, we are now able to get improvement in accuracy as well. Another topic I want to talk about is subset selection for efficient inference. I'll talk about two techniques here. One is a data dependent technique and the other is data independent technique. What's the idea here? I gave you a hint in the introduction that sometimes networks can be very complex, lots of neurons, lots of edges connecting those neurons to each other. Can we prune the networks, right, using core sets? So the idea here is neural network pruning using core sets. You can do either neural network pruning or compress them. They are analogous. So let's go through one work, which is CoreNet, which does this. It has a notion of data dependent core sets. What you're doing here is for each edge, you're computing its sensitivity, SJ. So each edge here, you're going to have a sensitivity computed. Okay. What is the sensitivity saying? Well, it's basically saying how in the subset of nodes that I or edge that I select in the first case, what happens if I don't have this edge? Okay, so it's a max over all the neurons X and S. Sorry, all edges X and S of the weighted sum of the WJ and the activation AJ on X. And based on this, you can now generate importance sampling. So you're sampling the edges based on the importance that you got from SJ with a suitable normalization. So you will basically sample weight the edges based on importance sampling distribution Q. This is a simple idea, right? Based on weight pruning happens here. However, the simple idea leads to some very interesting generalization bound. Basically, you get a guarantee on the approximation accuracy, the size, the generalization of the compressed neural network, how well you can do when you compress. So there's some interesting theoretical properties. It's also very computationally efficient, does not require retraining of the neural network, as you saw, just based on this weighted sampling, and easy to implement. But there's a data dependent core set idea, where you're looking at the activation AJ, right? Will come from the data. But can you also do data independent? We'll come to that. But you look at again the CoreNet performance, you'll find that the average drop in accuracy using the CoreNet idea, because you got a less efficient, less inference time, more efficient inference. However, the average drop in accuracy is low for CoreNet compared to some of the other approaches. So you'll find the CoreNet is always at the bottom, especially the dark blue one, CoreNet plus plus. So they have variants, and the shades you typically you see here are basically the values with one standard deviation of the mean. You can also have data independent neural network pruning via core sets. And what you're going to do for every neuron in the hidden layer is compute its importance. How important is that neuron, PRP? So you look at it before pruning and after pruning, and then sample the neurons according to the importance and reweight the selected neurons. So again, data independent pruning. Basically, again, you see that with 90% compression ratio, 90% of the original network, the error has, is very competitive. It's in fact very good, right, compared to the entire network architecture. So 2.03 and 8.16 as against 2.16 original ones and 8.95 respectively. So it's also leading to better efficiency. Very few parameters, much smaller number of parameters. That's what the 90% and 75% were about. I just talk very briefly about another very important aspect of data subset selection, and which is feature selection or compression. And there are different approaches to feature selection or compression. You can do information theoretic feature selection, There is this notion of weak submodularity in feature selection. And you can also talk about categorical feature compression and learning to features combinatorially. Okay, so why is this important? Well, it's important in machine learning to select the right set of features because you want to save on prediction time, especially when you have large deep feature sets. I mean, especially let's say I'm heading the Center for Digital Health at IIT Bombay, and the last thing we want is the network to just unnecessarily use features. So the general feature selection framework is you have the set of all features, you generate a subset, and look at how good that subset is, evaluate the performance, and then based on this, keep iterating and select the best subset. And many natural subset selection frameworks involve submodularity. Okay, so mutual information based feature selection, that's the first one. It's a simple idea, and I would say mutual information is based on this entropy, which is the canonical, kind of canonical submodular function. So you're trying to identify a subset XA of features which have high mutual information with the label Y. Now you can select this greedily, but this mutual information is not always submodular. However, when all the features are conditionally independent, then the mutual information is submodular. FA, that is mutual information. Okay, so that's a simple idea. I mean, basically, it's when you assume this naive-based assumption, then you get submodularity. However, in practice, things are often better than what we would expect. So even when the mutual information function is not submodular, it turns out that it's a difference of submodular functions. Okay, and that gives you a good approximation. Okay, so this what you see here is what several MI based feature selection frameworks do. MI is mutual information. They approximate the mutual information by breaking into two terms. One is a relevance term. Okay, so this is saying how relevant are the features with respect to the classes, and the second term is a redundancy term, how they are basically correlated with each other. So if one feature is very correlated with another feature, you probably want to drop it. Okay, so this is called MR, and this is so this is the idea here is maximize the relevance. The first term is basically saying, okay, max relevance, and the second term is saying min redundancy, because you are maximizing the negative. Okay, and yeah, so this, how does it work? I mean, it behaves pretty well. I mean, at least the conventional norm deep learning era, such approaches have been very effective. But people have also tried other approaches. Can we do feature selection in the presence of feature costs? If I'm doing medical diagnosis of patients, and this is as recent as 2020, it's possible that different features are relevant for different people. So let's say each of these, this is a patient, patients belonging to different clusters. These are patient clusters. And you can see fMRI, lab test, X-ray, genotype. These are the different features. So idea here is you cluster patients based on observed features like demographics, and use the mutual information to do a joint training of the model in conjunction with the features that you're clustering. So you're clustering, you optimize for the features, and then you select do the feature selection, and then you learn your model, and so on. This is also connected to weak submodularity. So what you can also do is maximize a loss specific objective. Like for example, if you're doing linear regression, you can find a subset of features such that the resulting model has the highest R square measure. So you want to do an R square specific objective. So as I said earlier, there's a notion of weak submodularity. So this function f, which is the max over the L on the support set minus the L over the empty set, the log likelihood, this is weakly. So the support set is the support the subset of the set of features, and L is when you have the empty set. So this is weakly submodular if L is restricted, smooth, and strongly convex. Again, important properties of that are used for convergence. So as you can see, in terms of accuracy, how this helps, the feature selection based approaches lead to generally higher likelihood. You can see the ones in green here, they are leading to higher likelihood relatively than those which are oblivious. And not only that, if you have weak submodularity, you can get approximation guarantees as well. I talked about 1 minus 1 over E. Over E when in general submodularity, greedy algorithms of submodularity. But here you can get 1 minus E raised to minus M by M. So this is the convexity and smoothness parameters, small n and capital M. Okay, and then the final we come to is categorical feature compression. So imagine that certain user ID has certain features, but you can compress, like you can bring together features corresponding to say different geographic regions. The model could do that. So therefore you have China, Japan, Korea as one cluster, or Brazil and Argentina as another cluster. So this is another example. You're not just deleting, but you're compressing them. And you can parameterize this mutual information based on the clustering C as a submodular function. And there's a quasi-linear time algorithm which gives you this 1 minus 1 over E approximation as well. So we've ourselves done a lot of work on learning composition of features. For example, if I'm trying to learn a model for classifying cars, I might be interested in conjunctions of features. As you can see, these are conjunctions, two features together. Now the problem is akin to learning a subset of a large lattice. This is what you see is a lattice of different compositions, feature compositions, and this is a subset of that large lattice. And it turns out that this problem is analogous to, or can be has a convex relaxation. Okay, in the case of certain loss functions, you can have a convex relaxation, and convexity can itself be subject to very efficient algorithms. So we have a very efficient mirror descent algorithm for solving. So we have done a lot of work on supervised subset selection over lattices, where we have efficient mirror descent algorithms on the dual. Use this generalizes to multi-class, multi-label sequence labeling problems as well. However, all this has been also studied more generally under submodular minimization via Loa's extension. This is work from Francis Bach. There's very nice kind of monograph from Bach on this topic. I only talked about the specific aspects where we look at feature clustering. Okay, so this was overall an overview of how you can do data and feature subset selection towards efficient learning. We have a platform called decile.org, and it stands for Data Efficient Machine Learning. It's an open source platform. It features several modules such as submodlib, CORDS, which is for core sets and data efficient learning, Distil is for active learning, Spear is for semi-supervised data programming. So you're welcome to visit this. The whole intent is to present to the entire community in India and elsewhere who want to operate on deep machine learning, serious deep machine learning, but want to do this under data or resource constraints. And we have had lots of papers around the work. We have and lots of applications you can find on decile.org. Our applications in video surveillance analytics, which has also got a lot of press coverage for its impact in several places. We're using this in our machine translation ecosystem called Udan. Again, that also had a lot of press coverage last year. So all of these are hyperlinked from decile.org. So it's being used. That's very exciting. So I request everyone to go and I didn't talk about all the data efficient learning parts. I talked about largely about efficiency, robustness, and then feature compression. Thank you again for listening. Some bunch of references at the end.
Yeah. Thank you, sir. Thank you for your nice talk. Maybe we can take a couple of questions from the participants. Please, you can unmute and ask, or you can just write in the chat box.
I'm looking at the chat box and these are questions.
Okay, they will maybe asking me, sir, I have a couple of questions, maybe I can
Sure.
ask, and you can go ahead with the other question. So two
Sure.
questions. One is that how can we decide? So you talked about the pruning, okay, like network pruning. So how can we decide the percentage of pruning in each layer? Because that will affect in the accuracy. Maybe in manually we can decide 10% pruning in each layer. So how we can decide? And another question is that can we improve the model accuracy with pruning? Okay, we are still pruning, but can we improve also the model accuracy?
Very good question. So you're talking about network pruning or data pruning or both?
Network pruning mostly.
Okay, so network pruning. See, I think unlike data pruning, network pruning is best done if you're also cognizant of the problem, right? If you have, fortunately, there's been a lot of semantics associated with different layers in a neural network. The first layer might be helping you find the overall, just the pixel way based information. As you proceed, you get edge based information, and then you get larger sketch based information. So I would say that pruning should be done in a little wise manner. Network architecture pruning, and therefore instead of putting all your budget into pruning on one layer, maybe it's a good idea to prune across layers, right? So too aggressive a pruning may not be helpful. Unlike data, I think aggressive pruning also can work pretty well. So as far as network architecture pruning is concerned, I think it's best done with a little bit of domain information. And if it's done in a layer-based manner, I mean, some amount of budget per each layer, that will be helpful. The analog to this is classes, right? So if I do data subset selection, there also instead of doing subset selection in general, if I do subset selection on each class, I can make sure that certain classes are not just getting underrepresented. So that's the analog of your question for the data part. So again, I think some domain knowledge is important here, whether it's class information for data subset selection or whether it is layer information for the deep neural network architectures for subset selection there.
Okay, thank you,
Does that
sir.
help?
Yeah, okay.